Slope fields. Objectives. By the end of this lesson, you should be able to understand that a slope field represents a family of solutions for a particular differential equation, graph a slope field given a differential equation, match a slope field with its differential equation, and match a slope field with the family of solutions to the differential equation. Definitions. Slope field. A slope field is a visual representation of the family of solutions given a differential equation without an initial condition. So when I say visual representation, we're going to be constructing a unique type of graph that represents the family of solutions given a differential equation. Let's take a look at an example. Solve the differential equation dy dx equals 2x, then construct its slope field. So this is a really basic type of differential equation that we can solve, but soon we're going to get to differential equations that we cannot solve for explicitly, and that's where slope fields are going to come in handy. But this is a good basic example to try to understand the purpose behind slope fields. So first we're going to solve this differential equation. So we're going to have dy dx equals 2x, multiply both sides by dx. So the dx's cancel. I have dy equals 2x dx. And then I'll integrate both sides. On the left, I have just y. And on the right side, the antiderivative of 2x is going to give me x squared plus my constant c. So now the idea is that I want to be able to graph this family of solutions. Well, since I was able to explicitly find the general solution to the differential equation dy dx equals 2x, that's just x squared plus c, this differential equation, it's not really necessary to construct its slope field, because if I wanted to draw the graph of this family of solutions, well, that wouldn't be too hard. X squared plus c is going to be a parabola, and this plus c is going to give me a vertical translation. So just as a rough sketch, if I wanted to go ahead and draw the graph of the family of solutions, well, when c is 0, then this is just the graph of x squared. Whoops, I missed the origin. So this is supposed to be y equals x squared, actually going through the origin. If c is 1, then this entire parabola is shifted up 1 unit. So we can go ahead and draw that. So x squared plus c is the entire family of solutions where the y-intercept is adjusted along the y-axis. But let's just say we couldn't figure out the general solution to this differential equation. We didn't know that it was going to create a family of parabolas. So now let's go ahead and construct the slope field for dy dx equals 2x. Alright, so here's my differential equation, dy dx equals 2x, and this is the grid that I'm going to create my slope field on. So I did say it was a unique type of graph. There's still an x and a y axis here, but now at every single coordinate point there's this little dot, and it's going to make sense why these dots are here in just a second, because to create a slope field I have to create an entire grid of tiny little slopes at each coordinate point on the graph. So here's my differential equation, dy dx equals 2x. Now I want to think about the slope at every single point. So let's start at the point 0, 0. So dy dx at the point 0, 0. Well, dy dx only has an x in it, so if I substitute in a 0 for this x, dy dx at 0, 0 is going to be 2 times 0, or just 0. So a slope field is going to represent the slope at every point. Well, at 0, 0, the slope is 0. So a line with slope 0 is horizontal. So right at 0, 0, I'm going to go ahead and draw a tiny little line with slope 0. Let's try another one. So let's go ahead and try this coordinate point right here. Each of these little tick marks is 1 unit. So this coordinate point is 1, 0. So dy dx at the point 1, 0, well, now the x value is 1. So 2 times 1 is going to give me 2. So at this point 1, 0, I have to draw myself a little line with slope 2. So let's go ahead and try to make it a line with a little bit of a steeper slope than 1. So this is my line with slope 2. So now let's move on. Let's try the coordinate point 2, 0. So dy dx at the coordinate point 2, 0. Well, now the x value is 2, so we're going to have 2 times 2 is 4. So now this has to be an even steeper slope than the one I drew right here at 1, 0. So it has to be a little bit steeper without being a vertical line. So let's go ahead and do another. Let's move on to negative values. So let's try what's going on with dy dx at the point negative 1, 0. Well, now I'm going to have a slope of negative 2, because I'll have 2 times negative 1 is negative 2. So over here I have negative 2 as my slope. And so you can imagine if I plug in negative 2, 0, well then I'm going to have negative 4 as a slope. Well, I don't just do all the points along the x-axis. I have to do every single one of these coordinate points. But in our example, this is not going to be too bad because all of the points, let's pick this vertical line here. The x-coordinate, no matter what, on this vertical line is 1. So this point right here is the coordinate point 1, 1. Well, since this differential equation only depends on x, the slope at this point is going to be 2. And the slope at this point is going to be 2. And 2 all the way down. So along every vertical line I'm going to have the same slope because every single x-coordinate on this line is 1. And 2 times 1 is 2. So similarly, all of these will be 4. So I'll try to make those look like the same as the first one I drew. And it's really going to be a matter of being patient and trying to draw lines that are the same slope respectively, where you have determined the slope goes based on each coordinate point. So over here these should all be negative 2 because every single x-coordinate along this vertical line is negative 1. And then here these should be negative 4, so they should be a little bit steeper. All along the y-axis, every x-coordinate is 0, so every slope here will be a horizontal line. And then way over here at the outskirts, this x-coordinate will be 3, so 2 times 3 is 6. So it's going to be hard to not draw it quite like a vertical line. But I will try to make it even steeper than slope 4 without being vertical. So this collection of all of these slopes is a slope field. Now, if we had no idea that the solution to this differential equation, remember we solved for it above, was y equals x squared plus c, well now we might have an idea that that might be the family of solutions, because if you notice, if you look at this slope field, and if we had a more comprehensive slope field with more and more points, because there's no limit to how many times we can do this, we would get a very accurate representation of that slope field. So let's just go ahead and sketch one solution. Let's go through 0, 0, and we can see that if we try to follow the slopes, that we will have a parabola as one of our solutions. So our general solution is the family of parabolas where the y-intercept is varied. So this is a basic idea behind slope fields, but this one in particular seemed a little less interesting because we already knew that the family of solutions was a family of parabolas. But let's try a different one. In this next example, I want to focus on the differential equation. So the slope field for dy dx equals x plus y is given below. Note that we cannot find the general solution explicitly. So this is the type of differential equation for which you'll be asked to construct a slope field. And the reason for that is because we cannot find the general solution explicitly. So at this point, if we tried to make this a separable differential equation, we would not be very successful. So if we go ahead and pull it to the side and try, we have dy dx equals x plus y. We would normally try to move the dx to the other side to end up with dy equals x plus y times dx. And then we might think to distribute in the dx. So we'll have x dx plus y dx and the dy on the left. Well, now if we go ahead and move the dy dx to the other side by subtraction, we'd have dy minus y dx equals x dx. And here's where we're stuck. So on this left side, I can't factor out a y, so this y is stuck to this d, so that's one whole thing here. So I cannot factor out a y, can't factor out a dx, so there's no way to isolate all of the variables with y on the left and with x's on the right hand side. So this is not a separable differential equation, so I cannot explicitly find a general solution. However, here is the slope field for the differential equation. So I know that my family of solutions looks like it would take on the form of these curved lines here. So the family of solution is going to vary by a constant, so that's why the curved lines sort of follow the same pattern over and over again. And this is a much better slope field than the one we constructed because it's been done by a graphing calculator unit. So slope fields give us a really good picture of what the solutions are going to look like. So this function here, it doesn't look like one that we can identify. It's not simply x squared or x cubed or a function that we can easily recognize, but it does at least give us a glimpse of what the family of solutions looks like. So informally, it's going to be useful to think of a differential equation as a set of instructions that tells the solutions which direction to go in at each point x, y. If we draw each direction as a tiny little slope at x, y, then we're going to have a collection of slopes known as a slope field. Sometimes you'll see it called a direction field that gives us a visual representation of the family of solutions to the differential equation. So that's going to be a really useful way to think about a slope field. So now we're going to go ahead and try to construct a slope field, not quite with this much detail, but one that was a little bit more challenging than the first example. Alright, so in this next example, we're going to draw the slope field for the differential equation dy dx equals x minus y. So similar to the last example, we cannot rewrite this to be a separable differential equation and solve explicitly for the family of solutions. So instead, we're going to draw the slope field, and this one's going to be a little bit more time consuming. So we're going to have to plug in x values and y values this time. So let's go ahead and start with 0, 0. So what is the slope at the coordinate point 0, 0? So if we plug 0 in for x and 0 in for y, we'll have 0 minus 0 is 0. So right at the origin, 0, 0, I'm going to draw myself a little slope that is horizontal. Alright, let's move on to 1, 0. So dy dx at 1, 0. The x value is 1, the y value is 0. 1 minus 0 is 1. So I'm going to draw myself a little line with slope 1. Now we can move on to 2, 0. So dy dx at 2, 0 is going to be 2 minus 0, which is positive 2. So now I have to draw a line with a little bit of a steeper slope than 1. So there's my line with slope 2. And then we can sort of see the pattern here that this line is going to be a line with slope 3 because I'm going to have 3 minus the y value of 0. So I'll make this a little bit steeper here with a slope of 3. Alright, now let's see what happens at 1, 1. So dy dx at the coordinate point 1, 1, well, I'm going to have to plug a 1 in for x and a 1 in for y, so 1 minus 1 is going to give me 0. So at the coordinate point 1, 1, I'm going to have slope 0. So similarly, at the coordinate point 2, 2, I'm going to have slope 0. And at 3, 3, I'm going to have slope 0 because I'm subtracting 3 minus 3 and 2 minus 2. So how about down here at negative 1, negative 1? So negative 1, just to convince ourselves, we have dy dx at negative 1, negative 1. So we'll have negative 1 minus negative 1. So we're going to add the opposite, and we're going to have 0 again. So all along the main diagonal, I'm going to have little lines with slope 0. So now over here off to the left, I have the coordinate point -1 minus 0. So this point will have a slope -1. Here I'll have -2 minus 0, so -2. And then here I'll have the slope -3 minus 0, so I'll have slope -3. Alright, so let's continue. This coordinate point is going to be the point 0, 1. So I'll just write a couple of these out. So if I have dy dx is the point 0, 1, evaluated at 0, 1. Well, now my x value is 0, my y value is 1. So at 0, 1, I have a slope -1. And up here at 0, 2, I'm going to have a slope -2. And then up here, I'll have a slope -3. Down here at 0, -1, well, then I'll have 0 minus -1, so I'll have a slope of +1. And I'll have a slope of +2. And I'll have a slope of +3. Let's go ahead and try this coordinate point here is 2, 1. So what's going on at dy dx is at 2, 1. I'll have 2 minus 1 equals 1. And at this coordinate point I have 1, 2, 3, up 2. So 3, 2. 3 minus 2 is 1. So if we can sort of see this pattern, if I've drawn the line straight enough all along this diagonal, I'm going to have lines with slope 1. And now, by the magic of video recording, the slope field is complete. So you can see this isn't very difficult a process, just time consuming and a little bit tedious. So we take each coordinate point x, y, and we substitute the value of x and y in respectively into the differential equation and draw ourselves a little slope with that, a little line with that slope. So this is a bigger example. Not even the AP test will give you an example with this big of a grid. You will usually see a grid of 3 by 3 or 3 by 4 by which to construct a slope field. But a typical question is to match the differential equation with the slope field. So that's what we're going to focus on next, is matching. Alright, match the slope fields with their differential equations. So here are 4 slope fields and 4 differential equations. So let's take a look at the differential equations. dy dx equals sine x. So there's only one variable involved here, x. And the second one, I have dy dx equals x minus y. So 2 variables in part B. In C, I have dy dx equals 2 minus y. So only one variable here, and the variable is y. And in the last one, I have dy dx equals x. So one variable here, and the variable is x. So the nice thing about when I have a differential equation with one variable is that I can go ahead and solve for the differential equation explicitly, or the solution to the differential equation explicitly. So here, dy dx equals sine x, the antiderivative is going to be cosine x, or negative cosine x. So negative cosine x is a family of solutions. Well, if I look at my options to match it with, the only one that looks like negative cosine x is the last one. This looks like it's going to be an oscillating function. So this last slope field is going to match with A. So now I'm going to go ahead and skip the one that involves 2 variables for a second, and I'm even going to skip the one that has the one variable of y. So the one that has the one variable of x, though, that's another easy one for me to simply take the antiderivative of. The antiderivative of x is x squared over 2. So x squared over 2 plus c is a family of parabolas. So the only one that looks like a family of parabolas, well, that is the second slope field. So this one has the shape of a bunch of parabolas, so we'll say that this one matches with D. So taking a look at A and D, they were only dependent upon the variable x. So let's take a quick look at them. We said that A matched with this last slope field, and since it was only dependent on the variable x, along every vertical line, I have a collection of the same slopes every single time. So along the y-axis, I have all zero slope. Then I have all positive slope, more steep positive slope, the same negative slope. So every vertical line had the same slope when the differential equation only depended upon x. So similarly with part D, where only the differential equation depends on x, again my solution had all vertical lines with the same slope. So for part C, this differential equation only depends on y, so it seems like it would match the only slope field that has all the same slope in horizontal lines. So the only one that matches that is this first slope field. So along every horizontal line, there's the same slope. So if I just pick a particular one, probably this line that has all horizontal slopes, this point right here is going to be the point 0, 2. So if I plug the y value of 2 in, because it only depends on the y value, I'm going to get 2 minus 2, which gives me a slope 0. So I know that this slope field does match the differential equation 2 minus y. And then we just did this example, dy dx equals x minus y, and this was what our slope field ended up looking like. But if I didn't remember that, then I could just go ahead and plug in a couple of points to be sure. So looking at the slope field at 0, 0, if I plug in 0, 0, I get out 0, 0, 0 minus 0 as an option. So I know that the only remaining slope field is the correct answer, that this slope field does match B. Alright, so now on to another matching problem. The slope field from a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? So notice the difference here is that I'm given a slope field, but I'm not asked to match it to its differential equation. I'm asked, well, what could the solution to that differential equation be based on the slope field? So remember, a slope field represents a family of solutions. So here I have a collection of different functions, y equals x squared, y equals e to the x, y equals e to the negative x, y equals cosine x, and y equals natural log of x. So which one of these 5 solutions could potentially be a solution to the differential equation with the given slope field? So this is a matter of knowing your graphs, knowing the graphs of basic functions. So here, y equals x squared. Well, we saw what a slope field looked like that depicted a family of solutions involving x squared. And it definitely did not look like this little portion of a graph, because a parabola, so we can kind of sketch each graph below it, looks like a U. So this definitely cannot be made to look like a U, so the answer is not A. B, y equals e to the x. So the graph of e to the x looks like this. This is the graph of e to the x. So this does not match, this slope field does not match the graph of e to the x, so that cannot be a solution to the differential equation. Y equals e to the negative x. So this involves understanding and knowing reflections of a graph. So when I have a negative in front of the x value, then this thing reflects over the y-axis. So if this is e to the x, and here's my x and y axes, then e to the negative x reflects over the y-axis. So it's actually going to look like this. So y equals e to the negative x is going to have this general shape, which does not match the little portion of the slope field I see here, so the answer is not C. The answer is most definitely not D, because cosine x is an oscillating function, so it looks something like this, and that is not the graph that I see at all depicted in the slope field. But finally, y equals natural log of x. Well, natural log of x, we should know, looks like this increasing function, and it definitely looks like it could be one of the specific solutions to this differential equation. So the answer here is E, y equals natural log of x, could be a specific solution. But I want to focus on the difference. They did not give us differential equations to match with the slope field. They told us to match it with a possible solution to that differential equation. So 2 different really good problems involving slope fields. Alright, and now let's go ahead and look at the 2008 AP Calculus AB free response question number 5. So consider the differential equation dy dx equals y minus 1 over x squared, where x cannot be 0, because otherwise the bottom would be 0 and I would have something undefined. So on the axis provided, sketch a slope field for the given differential equation at the 9 points indicated. So here is your little grid that they will provide for you. So use the axis provided in the exam booklet to go ahead and draw the slope field. So at each of the 9 points given, so here are my 9 different dots they provided that I'm supposed to draw a little slope on each one. So let's go ahead and start with this coordinate point 1, 0. So I want to know what's going on with dy dx at 1, 0. So if I plug 1 in for x, then I'm going to have a 1 on the bottom. If I plug 0 in for y, I will have a negative 1 on the top. So I have negative 1 as the slope I'm going to draw on this little first circle at 1, 0. So negative 1. Alright, so now what's going on at 1, 1? So I have dy dx at 1, 1. So on the top, if I plug a 1 in for y, I'm going to have 1 minus 1 over, if I plug a 1 in on the bottom, 1 squared is 1. So the top is 0 over 1. And again, I can have a 0 on the top. That's fine, as long as there's not a 0 on the bottom, and there's not, so this answer is 0. So at 1, 1, I'm going to have a little horizontal slope with slope 0. So now at 2, 0, if I plug in 2, 0, I will have dy dx at 2, 0. So 2 is my x value, so on the bottom I have x squared, so I'm going to have a 4 on the bottom, and 0 minus 1, so a negative 1 on the top. So I have a slope of negative 1 over 4 at the coordinate point 2, 0. So I have to draw that as a flattened slope here at 2, 0. Now let's see what happens if I plug in 2, 1. So I'm going to have dy dx at 2, 1. So if I plug in a 1 on the top again, I'm going to get 1 minus 1 over 2 squared is 4. So I'm going to get 0 yet again. And then let's see what happens at 2, 2. So let's just go ahead and do this in our head. So if we plug in 2 for y, I'm going to get 2 minus 1. That's going to give me 1. And then, whoops, if I plug in a 2 on the bottom, I'm going to get 2 squared is 4. So at 2, 2, I have a slope of positive 1/4. So that's going to give me a slope like that. Here at 1, 2, if I plug in an x value of 1, it's going to be a 1 on the bottom, and a y value of 2 on the top, 2 minus 1 is 1, so 1 over 1 is slope 1. And then over here at negative 1, if I plug negative 1, 0 in, so negative 1 for x, the bottom is 1, and then 0 for y, the top is negative 1, so I have a slope negative 1. At negative 1, 1, if I plug negative 1 in for x, I get a 1 on the bottom. If I plug a positive 1 in here, 1 minus 1, that's going to give me out a slope of 0 again. And then the last point out of 9, negative 1, 2. If I plug in a negative 1 for x, I get a 1 on the bottom. 2 minus 1 is 1. So there's my slope of 1. So this is my tiny slope field. Thank goodness they only asked us to plug in 9 different points. So that is the answer to part A. Part B, find the particular solution, y equals f of x, to the differential equation with initial condition f of 2 equals 0. So they're asking us to solve a differential equation here. So this differential equation, y minus 1 over x squared, when f of 2 equals 0. Alright, so let's solve this differential equation here. Multiply both sides by dx. So I have dy equals y minus 1 over x squared dx. So now I need to get this quantity y minus 1 to the other side, so I'll have to multiply by 1 over y minus 1, or divide by y minus 1. So I get dy over y minus 1 equals, I'm going to rewrite the right side as x to the negative 2 dx. So I brought the x squared on the bottom to the top and made the exponent negative. Now I'll integrate both sides. On the left, I'll end up with the natural log of the absolute value of y minus 1. equals, on the right, I'll end up with negative x to the negative 1 plus c. Now let's solve for c using our initial condition up here, f of 2 equals 0. So when I substitute 2 in for x, I get out a y value of 0. So solving for my initial condition, I have natural log of 0 minus 1 equals negative 1 over 2 plus c. So let's go ahead and move that up here. I have natural log of 1, so this would be negative 1, but the absolute values make it positive, equals negative 1/2 plus c. Natural log of 1 is a value we should know to be 0, equals negative 1/2 plus c. Add the 1/2 over, c must be positive 1 over 2. So now let's substitute that back in here. This was our general solution, not yet solved for y. So let's plug it back in. We have natural log of absolute value of y minus 1 equals, I'm going to rewrite this as negative 1 over x plus 1/2. So now we have to try to get the y by itself. So we exponentiate both sides. So now this whole thing is up in an exponent. E to the natural log cancels, so I end up with the absolute value of y minus 1 equals e to the negative 1 over x plus 1 over 2. And now I just have to make sure that I choose the right option here when I use my initial condition. So my options are either just to remove the absolute value bars or make it negative the quantity y minus 1, and that depends on the initial condition. So if I plug, let's see, if I plug 0 in for y, I'm going to end up with a negative value, which I'm going to need to force to be positive, so that means I need to switch this. So this would have to become 1 minus y equals e to the negative 1 over x plus 1 over 2. And then I'll subtract 1 and divide by the negative. So I'll have negative y equals negative 1 plus e to the negative 1 over x plus 1 over 2. And if I divide by the negative, this becomes positive, positive, and this will be negative. So my final answer, y equals 1 minus e to the negative 1 over x plus 1 over 2. We can check our answer to make sure the initial condition works. If I substitute in 2 for x, this becomes negative 1/2 plus 1/2. So that's 0. E to the 0, anything to the 0 is 1. So 1 minus 1 is 0. That gives me out what I need, this y value of 0. So I know that this is my final answer. Y equals 1 minus e to the negative 1 over x plus 1 over 2. So that's my answer to part B. And then finally, for the particular solution you found in part C, or part B, find the limit as x approaches infinity of f of x. So here's y, or f of x, and we want to evaluate this limit at infinity here. So I want the limit as x approaches infinity of the function I just found, 1 minus e to the negative 1 over x plus 1 over 2. So as x values approach infinity, I have negative 1 over really big numbers, so this portion here goes to 0. So my answer would be 1 minus e to the 1 over 2. So 1 minus e to the 1 over 2 is the answer to this limit at infinity. So only this portion right here goes to 0 as my x values approach infinity, because nothing else has an x in it for us to substitute in bigger and bigger values into.